Hello, Professor. Today I will present the homework 2. The topic is Lecture 3 Summary. I am today's presenter, Jiajun Jiang. Here's the agenda. The first, I want to introduce the ISA, and then is how to execute a program, and then is different memories. We will discuss the different memory has different capability and speed or cost, and then is flag register, and is segmentation and the stack, and the last one is addressing modes. The ISA can separate to two different types. The first one is risk, and the second one is CISC. Those two type of ISA has different advantage. Like the main advantage for risk is the CPU execute efficiency, and the CISC not only have the basic instruction but also have some very complex instruction. So the CISC can provide the better coding environment for the designer. And the instruction cycle is mainly to do three things. The first one is fetch, and second is decode and execute. Fetch, decode, execute. We have to make sure the instruction can do fetch, decode, execute all the time. We don't want the cycle to stop. And every instruction will have opcode, because the opcode is to make the computer know which method or which arithmetic we want to use. So every instruction have a opcode. So for example, we can see the picture in the slide. There's a MIPS, and there's three types of instruction. Is R type, I type, and J type. J type is for jump, for branch. I type is for adding or arithmetic, and the R type is for two registers to do some arithmetic, and then to store in another register. Different systems have instruction coding types, like the ARN, RISC have fixed length, means each instruction have the same length. Like Intel 8086, it have different length, like it is a variable length for the instruction. We can also separate the instruction into 4 types. So means we use the instruction to do the 4 things. The first one is data movement, means we can move the data from A box to B box, and the comparison is obviously just compared to type of things, and is arithmetic and program control. Program control like the jump and the branch, some kind of things. And then is how to execute a program. Our computer only can understand 0 and 1, so we cannot just give a C program to tell the computer, oh, you have to know what I want to do now. So we have many steps to make the C program to convert to the 0 and 1. First, the high-level language will go through the compiler to become an assembler language program. And then we use the assembler to become the machine language model. And the linker is to connect a lot of model or the data to fix the address problem. And the last one is loader. The loader is put all of things in a proper memory address for execute. And then is different memory. The computer has 4 different memory. The first one is register, and then is caches, main memory, and SSD and HDD. The top is register, which means it is faster but very small. And the last one is HDD, which is very large, but we have to use a lot of time to access the memory. But why the CPU register? need a lot of register, why don't we just put more register into the computer so we can put the all of the very number into it? Because if we put too much the register, the decode time will be longer, and the CPU execute efficiency, the clock cycle time will be longer, so the efficiency will go down. So if we use the DAS, register can also reduce the CPU efficiency consumption. And then is flag register. The flag register, we have 16 bits, but only 9 bits to be used. So we can see there's a 7x in the flag register, and we can separate them to status flag and control flags. And I will introduce each flag register are doing what kind of things. The first one is CF. The CF is carry flag. So when we do the arithmetic, the most significant bits, if it is carry, we will set the CF to 1. If it's not, we will set CF to 0. And then is PF. The PF is to judge after the arithmetic. We can see if we have the oddest, we have odd numbers 1, we set the PF to 0. If we have even number 1, we set the PF to 1. And AF is after arithmetic, we can see the third bit. If it become carry, we set AF to 1, otherwise is 0. And ZF is 0 flag. After arithmetic, if the answer is 0, we set ZF to 1, otherwise is 0. And SF is sign flag. After arithmetic, we will see the NSB. If NSB is 1, we set SF to 1. So it will present the number is negative, otherwise is 0. Present the number is positive. OF means overflow flag. Obviously, if happen overflow, we set the OF to 1, otherwise is 0. And TF is trap flag to debug. Most of the time we use to debug. If the TF is 1, means the program will execute each single instruction at one time. And DF is to do the string calculation. If the DF is 0, when we do the string, we will start with the lowest significant string byte to the highest significant byte. If DF is 1, we start with the highest. The IF is interrupt flag. When IF equals 1, the CPU can accept the external interrupt. If IF is 0, we cannot accept the external interrupt. And segmentation is like we have different segment register like CS, SS, DS, and we have to put all the segment into a physical memory. But how do we know the address we have to put all the segment register in? So we have 3 types of address. The first one is physical address, and then is offset address and logical address. How do we know we have to put the code segment into the address? So here's the example. The example is we want to find the logical address, the offset address, and physical address, and the lower range and the upper range on different segments. For example, the code segment and data segment are very familiar, so I put segment and data segment together. So if you want to calculate the logical address, it's very easy. The question already gives us the code segment's address and data segment address, and he is instruction pointer, so we can use only 3 data, we can calculate every address we want. So if you want the logical address, you just put the code segment and the IP into it, so we can get the offset address is IP, and the physical address just put we have to left shift the code segment 1 bit and add the IP, so we can see we add the 66660 plus A, so it will equal to 6EE8 in hex. And the fourth is lower and upper range. The lower range we just add 0, so it will basically equal to the data segment. And the upper range we add the FFFF, because FFF is the most large number in hex if we only have 4 bits. And then is the stack. The stack is a section of read and write memory used by the CPU to store the temporal information. The reason why we need the stack, because we only have a limited number of registers, so we need the stack to help us to create more memory we can use. Every register can be stored in a stack using push, and if you want to retrieve from the stack, we using pop. So the last in, first out. We can see the picture. We put the number 1 first and the number 3 last. But when we pop, the number 3 will come out first. And how to calculate the stack is still same as the CS and DS. So I list the example here. We can see we do the same thing as the data segment and code segment. And then is addressing modes. We have 7 different type of addressing modes, and I will introduce every single one on the next slide. The first one is immediate mode. The operand comes immediately after the opcode, and the data cannot be moved directly to the segment register. Then there's an example. We move the AX 3333 hex. So it means we move the 3333H to the AX register. Second is register mode. It means use register to hold data. The example is move BX marks 3CX. It means we move CX data to the BX. And the register mode, we don't need the memory, so it is very fast. And the third is direct addressing modes. It means we move, if we see there's a hit, if we see a bracket, and it means we have to find the address location. So the example in the third is we have to find the 1133 address data and move to AX. And the fourth mode is register indicator. We also see this brackets in it, but we put a data segment in a bracket, we have to find out the data in the segment register, and then we go to find out the address and put the address data into BX. And is the 5 models. The 5th model is basic relative modes. It is still very similar to the 4th. The difference is we can add or sub some number after we find out the address, so we can adjust. We want upper data, we can just add 1. If we want a lower data, we just minus 1. And the 6 and 7 is still very similar. We just add 2 register or just add more number on the bracket outside of the brackets. So for a 7 is just add to register and an integer to obtain an address and find out the data in the address, then put into the AX. And that is all I have today. Thank you, Professor. And here's the reference. And most of the resource I found is on the wiki, but sometimes I will summary and draw on the iPad for myself. So the reference I use is only 2 because I just used the 2 picture on my PowerPoint. So thank you.